we're trying to reverse engineer a theory of everything, or a computer structure that's universal in the sense that physics is universal, right? So those are our main goals. In order to accomplish that, we have to get to a point where we can conceive of the inner structure of physical reality, conceive of the boundaries of the actions of all the things that are actually happening in all the physics actions. So all the equations of physics, all the constants, so on, are referencing some sort of connectivity fixed into nature that we've spent a lot of time and effort and conceptual revolutions to get to, right? To get the data points of. No one yet has come to an interpretation of how to make sense of those data points, right? Those mysterious facts about nature, like that the speed of light is this exact specific speed, right? That there's 5 coherent bases of reality, one for time, one for space, one for charge, mass, and temperature, built into the structure of everything we measure, everything made out of atoms, okay? These are big clues about what nature is. We haven't really tied it together to a story, and we're going to need a clear, comprehensive story, one we can picture in our minds, one we can make animations of and discuss and point to specific characteristics and very detailed analysis of, but then very detailed taking advantage of the structure and inbuilt connectivity, differentiation, integration, all of the richer internal structure that we're intrinsically missing right now when we model, say, quantum mechanics in an indeterministic way, in a probabilistic way, right? We're average overing the actual state with a description that says, taking into account the whole probabilistic states that could possibly be, given ignorance entirely of where things actually are, and then treat that collection of states as the state vector, as the fundamental descriptor of reality. That's really a blurring of logic already. You're blurring what you can describe now. And it's really kind of a move you have to justify hardcore if you're going to take it, because it really causes damage to another entire foundation of logic you've been resting on. All of it. Okay, why am I going with that? Well, we're following the prescription of taking the data points, all of the measurements listed at CODATA, for the physical characteristics of nature, all the parameters of quantum field theory, or the constants of nature, right? These are the treasures that have been hard won by physics. The entire history of physics has brought us to these, literally. That's the concepts that brought us to even the ideas to look for these traits is the history of physics, okay? So are we done? Do we have all the traits? We're never really in this position to be able to say something like that. But right now we have a large list, a set of physical traits that looks for so far to be able to account for all the things that happen in chemistry and in biology and on the way up. Okay, it's very interesting that we have a large collection of traits. We have measurements for the values of those traits. We have the dimensions for each of them, meaning the dimensional relationship that number is associated to for each trait. And yet, we haven't figured out a story, a geometric picture, algebraic structure, any kind of story that you can penetrate with your mind about why those traits are there, about what the relationship between those traits is that makes them all in this system. Why are any of them there? They're just all mysterious data points at this point, which makes them really interesting, right? In fact, I can't imagine what other things would be more interesting. These are the mysteries of quantum mechanics, the mysteries of relativity. Why is the gravitational constant what it is, right? These are the mysteries built into reality itself that allow the structure of the atoms that make you up. They're really, 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 really interesting mysteries because they're right there, a collection of mysteries that science has made right now, okay? Hundreds of data points with measurements and error bars so we know how much to believe it. Hundreds of these data points about what reality is, about the transforms and exchanges of energies that are allowed in the things made up of matter. We know a lot of stuff, a lot of data points, and we don't know what it means. We don't have a picture. Now, there has to be a picture. That's the whole point of collecting all this data, is that the data points revealed, first of all, what? Whoa, big first thing was that there's 5 dimensions. 5 dimensions that are doing something coherent. In things made out of atoms, there's 5 important different bases, actions that are playing roles together to make these balances that we call atoms. Okay, there's 5 important bases. And when we use the constants of nature, measurements, to peer into each of these different expressions, the bases that get revealed, the relationships of every constant of nature is a relationship between these bases. So the bases get revealed by our measurements. We get to sharpen what the actual natural base is. I know this is a big thing that's not popular in science to pay attention to yet. The philosophers of physics have maybe caught on a little earlier than most of the physics community, but it's right now, I think, really rooted in when you think the meter is a randomly picked base, right? Because we were all taught the first kindergarten story about the meter, because the first definition of the meter was that it was so many, a distance from the North Pole all the way down to Paris, divided by a certain number, and then it's the meter. A really arbitrary sense of distance, unless you think the size of the world exactly at this point in history is some magical size, right, number. And then the number we divided it by was some God-given, mystical, informed number. But it just seems really like the meter had nothing to do with anything real. And then most people never came back to that conversation. That was what you think the meter is for the rest of your life. And that's understandable, unless you're a physicist, of course. Because really what the meter is written into the questions we're asking in physics. It's right there at the core. What is the meter? What is the second? What is the coulomb? What is the kilogram? What is the Kelvin? What are the bases of measure that we're using? Now remember, we're using coherent bases. So the story of physics has been the story that has unwound what those bases were. So we started first with distance base, the meter, with a pretty random measure. And then we measured all these constants of nature. And from the constants of nature and the equations of physics that connect them, we found that the connections between all these constants of nature imply cutoff bases in dimensions. The connections between the constants of nature, between the relationships of different dimensions in different actions in physics. In order for them to be compatible, in order for these different expressions to be compatible, they imply a base of compatibility. You were implying earlier in a video you did last, we needed F equals ma, right? You wrote F equals ma. What does this mean? We're implying right now that the dimensions of force are built up of the dimensions of mass and the dimensions of acceleration. But we're also pointing out that there's no other weird number like 2.6639 in front of it to convert. There is a number in front of it, but it's 1. That's why it's coherent. The dimensions themselves arrange into other expressions of dimensions that are useful and built into reality. That's what coherent means. All of the different dimensional expressions that we care about, and there's lots of them in physics, they all have equations that connect them that have coefficients of 1 out front. They're all coherent equations in this coherent system of units that we're revealing by the constants of nature. We're finding these laws from the constants of nature, the rules built in between them, right? They're all surprises. These things exist. Some of them more obvious than others, depending on how much you've investigated reality so far. But the fact that there's built-in relationships between all these properties, these different expressions of properties, relationships of dimensions. Okay? So we've taken all of our data points and all of the dimensions, right? Strings of digits, powers, dimensions, and we've tried to interpret the coherent system of dimensions that the whole thing's talking about. How do we do it? Well, from the data points, we're assuming that everything is a two-piece picture. So when we have the data point, the speed of light is 2.99792.458 meters times 10 to the 8 meters per second. It's important to become aware. It's not very common to be aware of this, but it's a very important detail to be aware of. The units we're writing here, meters and seconds, are part of the story explicitly. I'm not saying that you can't convert this into feet per hours and give me a number. Of course you can. I'm just saying the number you gave me wasn't a coherent constant of nature. Because that translation, when you try to plug it into this other system of equations we have everywhere else, doesn't work everywhere without some coefficients that go crazy, some non-ones. That's what I'm saying. You can do all kinds of translations that you want, but the ones that are coherent to the system are meters and seconds. So we've been changing the definition. Now our definition comes from the constants of nature. Right? Our definition of the meter and seconds both directly relate to our measurement of the speed of light. Now, that's our modern definition. So what we mean now by meters is not at all in science, in physics, what we used to mean. We're not referencing some proportion from the North Pole to Paris. Okay? It's not a random thing anymore. The meter itself is a unit, a base, revealed by the division structure and connectivity of all the constants of nature and the rules of physics. Okay, when you look at the poster, you see that the meter shows up in the constants of nature, in the rules, in that whole pattern there. The meter shows up several times in relationship with other things. The second shows up several times. The Kelvin shows up, right? So the pattern's really gorgeous. I don't know how many people have spent time looking it over yet, but it's worth all the time you can give it. We looked at every single constant from CODATA. It takes a long time, right? So it's a big deal, but we use all the data points, their scales, the dimensions they're putting in relation, okay? And we translate them all in one simple prescription. So our constant of nature, for any constant, here's one example, the speed of light. We take the prescribed number and we would put that here when we're trying to solve this, okay? It equals some primary partition action or external partition action. I'm going to do this a little different than I've done before. So I'm going to call it a partition action and it's external, EXT, okay? And that's going to be on or some partition boundaries and these are always going to be made up of they're Planck relations. So meters are going to have a cutoff and it's going to be the Planck length. Seconds are going to have a cutoff and it's going to be the Planck time. Meters and seconds having their cutoff. I'm saying we're assuming now in the connectivity of the rules themselves and the constants themselves, there's implied cutoffs, discretion cutoffs, where the notion of that thing dissolves beyond it, right? So the thing you're thinking of that's time is, and seconds is the base of that thing, okay? Beyond the Planck time, which is a value listed in seconds, okay, 10 to the negative 44-ish seconds. Beyond that, there is no notion of the thing we're calling time, whose base is seconds. Why is its base seconds again? That was a mystery revealed by the constants of nature. We're not picked, okay? We're choosing these bases because these bases are the ones that you can use in all of the physics equations. Why would you want different bases? Those are the important bases. That's why it's important to reveal the bases as sharp as you can. So we need a really sharp definition of the meter and the second. Notice, if you're defining the meter and the second, which we are in today, right now our definition is based on for meters and for seconds, both directly based on the speed of light, then your precision can be how accurate?
Well, that's 9 digits.
9 digits. So if we're trying to talk philosophically about things to 50 or 100 significant digits, and we're trying to have a mathematical or philosophical conversation to that precision and map it to things we've measured in nature, we can't, right? There isn't that much mapping. We've never mapped something beyond 14 significant digits for any measurement of any trait of any kind. That's a really big thing to notice. That there's a precision limit that we've got so far, maybe built in or maybe just where we're at, but there's a limit. And it's only at 14 significant digits. So when we're showing digits, 14 digits means you've reached the limit of physics and now you're in mathematical possibilities, right? But you can't check, or at least so far. That's very interesting. This limit also implies that the base is filled by its inversion, meaning that the second itself, if you have 1 over the TP number of Planck times, then you equal 1 second. Do you see what I'm saying? So we're talking about a thing, the universe is a construction of some sort composed of at least 5 dimensions. The 5 dimensions are the 5 ways it is divided up. The 5 bases. To be a base, you have to divide 1, right? Independently from other things that divide 1, which means you have to divide 1 in a different way. The second is its own base. But this is why it's the base, because there's a cutoff, right? Because the base we're using to describe that cutoff is the one that's the coherent system base, and if you fill things with that number of Planck times, you get a second. Anyway, the other implication here is that the lifespan of the construction of whole complexity levels, the smaller chunks of pieces and the bigger, with smaller pieces with many more of them, the whole complexity of the whole structure is still going to be quantized. It's not going to be infinite. It'll be finite, right? And you can ask, what's the total lifespan of all the pieces? So if you want every possible inversion in the system to happen, everything to play out that can possibly go, what's the total lifespan before everything has now come back to exactly where it was? Right? In a quantized structure, it's a very legitimate question. You want to know, give me the feedback about how quantized it is. Like how much available space in this quantization is it? If it's not as quantized, if there's only so many pieces in the internal structure, then it's less quantized, and is the number of things and steps you can do before you completely come back to the system, if it's closed and invertible, then will be less, right? Well, this lifespan is going to be this number in seconds, right? We're dividing the entire system. We're having a projection that balances in that base and 4 others, but it balances that base into the projection, and it divides the base all the way down to the limit. But it means that on the reverse side of things, that the lifespan of the whole thing will have to be that in seconds, that number in seconds. All right, so now I need to come back to the second half. So this is our external half of our connectivity geometry. We got an internal structure and an external structure. They're balanced on top of each other. They're connected to each other. This is going to be the logic how we tear that apart. There'll be a partitioning of some kind. There'll be a geometric action. Okay. There'll be boundaries that's applied to. So these are connected together. That's why they're both external. And then we're going to multiply that to get the product of these two things. 1 plus some partition that's internal, and the internal inversion boundaries. Should draw that better. That's our symbol for it right now. I should always do this. Is equal to the Planck length, the Planck mass, over the Planck charge squared. So our story that we're unveiling is bipartite, right? It's two-piece. We're taking a two-piece structure. We're using those pieces to claim a balance in the transform, okay? And then we're trying to interpret them geometrically. So with this one exchange on this fixed internal boundary of inversion, okay, we've translated every constant of nature to get that pattern. Okay, and I know those following us are probably really excited about the things they've noticed in that pattern themselves. Okay, but what I want to do today is to reiterate now at what we're interpreting. We're talking about the hidden structure of reality, and we're lensing it in a new way that's never been done before, I presume, right? And finding a pattern that is phenomenally connected to the foundation of number theory. One. That's really interesting. Also, the story is that the structure of this entire connectivity and the rules of physics and the expressions and so on is just the structure of hyperbolic space. The rules built into hyperbolic space. And what that looks like is what's been absent from our mind, right? What does an n hypersphere look like? How does it divide internally? What are all of its parts? Who knows? Who can you go to ask? I don't think anyone has a picture of that. That's what's really missing, because what we interpret now from doing this process, right? We've done this several times in a few videos. We're going to do it again in detail in a future video, right? For a few constants of nature and talk about the poster and so on. But right now, what I want to mention is the thing that this is heightened for us is we want to intimately know what the tiny internal texture details are of hyperbolic space. Everything we can about hyperbolic space. So we're now motivated to know how these expressions are built into reality. We're motivated to know hyperbolic space itself. And what does it mean to know hyperbolic space? Well, the introduction that most people already have, by hyperbolic space right now, I'm really referring to, well, the entire construction of the conics, so circles and ellipses and parabolas and hyperbolas, but also the inversions, right? Cardioids and the lemniscate of Bernoulli. Okay, so the hyperbolic geometric bounds, what their shapes are and everything. Okay, we're interested in all of those. So to make that even simpler, let's break it down. The people who are interested in geometry, right? We got circles, ellipses. They're right here. Circles right there in the cone. Ellipses. If we turn the angle, the cross sections of the cone, it shows up there. We got parabolas, and we have hyperbolas. And then as inversions of parabolas and hyperbolas, we have the cardioid and the lemniscate of Bernoulli. Okay, so these structures are all intrinsically important for us now to understand. All of them are built in. So let's start with something simple, the circles and the functions. I'm calling all of these hyperbolic functions. Okay, so circles are hyperbolic. Ellipses are hyperbolic. They're all literal bounds built into the hyperbolic structure. Okay, and I'm interested in knowing all of them. So now we're going to start with the simplest of them, though, to understand hyperbolic functions. And one of the hyperbolic functions everyone is kind of familiar with would maybe be sine. Right? Sine is a very familiar graph. Starts here at the origin, and it goes up to a maximum height of 1. It dips down to a maximum dip of -1. It crosses back here at pi, and it crosses again at 2 pi. And then it repeats. So it's like the unit wave, right? Or the cosine, which starts quarter phase off of that. All right. This is usually the way we look into the sine. But today we're going to look into the sine and the other hyperbolic functions, which are what? Cosine, tangent. These are maybe the three first ones people are introduced to. And then I also want to do the hyperbolic sine and the hyperbolic cosine. And these are all just relatives. If you haven't been introduced already, they're very simple relatives, hyperbolic tangent, to the ones above. So these 6 first hyperbolic functions, the ones that are on your calculator, this is the way we usually look into them. And we know these features, 1, 1, pi, 0, pi, 2 pi, we know that's built in. And recently we've been mentioning this length right here, right? This arc length of that wave, of that cosine wave is, I'll label it that, the arc length of the cosine wave, or actually I did the sine, sorry. I should do sine. They're equal. It's still the same. Arc length is 4 pi divided by s plus s, where s is the, let's see, we have a cardioid and a lemniscate of Bernoulli. The lemniscate of Bernoulli is, instead of being the unit circle that we're dividing things up with, like into sines and cosines, by the way. So the circle here, I was breaking into sines and cosines, but now I want to look into the functions themselves, okay? But we also have things like this guy is supposed to cross in the middle there, and this is supposed to be 1, this is supposed to be -1. This is the lemniscate of Bernoulli, the unitary lemniscate. Okay? Like in the unit circle, this is the unit lemniscate. Okay, so let's do it. Instead of looking just at this two-dimensional construction of the sine, okay, let's up our game a little bit and make it so that we can see more of what's going on. Now, just to prelude what I mean by see more of what's going on, in every graph there's way more than what we show right away. Okay, let's draw that. Let's do a little thing right here. In our sine graph, okay, start it like that. I blew it up a bit. If we pick a point, any point on the sine graph, we can say that there's a straight line, a tangent, that touches that point and approximates the slope best at that point. Right? There's a straight line that keeps going straight even though the curve doesn't. And then later there's one over here. It's more like this. Okay? But there's also, so that was there to begin with, and it belongs to every single point in the graph. They already all have their tangents, but if you didn't draw them in, they're still there. But they also have tangent conics. They have tangent circles. In this case over here, the tangent circle is going to be on the inside, right? It's going to be a big circle like this, touching this point here. And then as it comes up here, it's going to become a smaller circle, touching this point here. And what changes the size? The curvature of the graph. If it's a really steep curve spot, then it's small. And if it's really flat, then the circle becomes infinite in size if it gets all the way flat, right? Okay, so the cool thing is not does only every point have its own tangent, it also has its own conic tangent. And if you trace, each conic tangent has its own center point, right? If there's a circle touching that point, there's a center of the circle too. Okay, that's another interesting point. But what about if you go a little bit this way? Well, then now you have a circle a little bit different and its center is a little further over it. Follow all of the paths of the centers and you trace out a new path that's related to the first path in a very intrinsic way, a very built-in, beautiful way. What we want to do is visualize the structure in the graph. So we have a great tool, Wolfram Alpha, right, to look at the surface plots of functions. So let's start by looking at the sine of x, and let's see how far we can go to visualize that function in a richer way. Now, everything we're going to see and say is true at the same time about this function, okay? But the visualization is new, at least for me, and I think it's going to be exciting for everyone to see it. Okay, so we go to Wolfram Alpha, and we just put in sine of x. We'll start there. And it doesn't know exactly what we're asking about this function, so it's going to list everything it knows that's directly related to the function we asked about. It gives us a little plot, right? Quite familiar. Zooms out, gives you a different view of the plot. It tells you another way to represent the function in exponentials, right? It tells you all kinds of things about this function, right? Beautiful. It's fun to follow this path if you're frightened of math or it intimidates you. It's a path you can follow in private, and you can just get interested in different aspects. You can be introduced to them for the first time. There's a reason they were all organized in there. So as you get familiar with what's there, you're going to start intuitively start absorbing how math connects in a lot of ways. So it's a fun feature to follow. But let's go a little further. This is the way we usually try to plot sine. There's nothing really wrong with that, but there's more to find if we assume the argument of the function is richer, a two-dimensional one. So we just go in here now and say plus iy to make it just a two-dimensional argument now so that the picture can be richer. And now suddenly we see something more, right? A lot more. It's also something that you can intuitively relate to more. Imagine that you were roller skating or skateboarding or mountain biking on a surface like that. Okay? You can relate to that. You can make sense of the surface and the drop-offs and everything. They have meaning because they're spatially arranged for you. Okay? This is a great thing. It's another way to relate to a function by making it geometric and spatial. All right, and these are the real and imaginary plots. That's what these were too. But here they're 3D plots, and here we're looking straight down on those plots. Okay, so we can see the division structure. It gives you the complex map, how we're changing from this XY normal grid that we're used to working in to this kind of grid under that function. Okay, beautiful. Okay, more information, but this is the visuals of what I'm after right now. Now, there's more. We can take this same function and invert it under circle inversion. And the way we do that is by taking its own argument and just inverting it. 1 over x plus iy. Now this is a circle inverted, a projection of, or turn it inside out, say. The same exact structure, same exact function, looked at from the other side of things. And look what you see now. Something quite different. Before, everything was striped and going off the page. Now it's kind of localized in the center. The distortion that's happening is something that's a different thing to skate around than before, right? All right, then you can zoom in, right? You can pick a different scale. Let's do that a bit. Let's say we want to zoom in from x being, what are we at now, 4? Let's just do 1 to 1, from -1 to 1. All right, you can see a little different texture resolution on the inside there. As you zoom in more and more, let's go 1 over 100. That should make quite a difference. I see a little different shape in there, but I was expecting more. Cool. Anyway, you can zoom in and look at this, the information of this surface plot. And I really recommend doing it. Play around with it, get familiar with any function. Start making up a function and start playing with it. See what changes when you change things in the function. That's a way to get comfortable with functions, but it's also kind of beautiful, right? It is beautiful, and you can make your own shape. Maybe you can play around with functions with the intention to make the coolest looking surface. Okay, but other than surface plots, We also can do a phase plot, right? Wolfram doesn't yet have the switch to phase button, but maybe that'll be a feature in the future. It's one I definitely would recommend. It'd be beautiful. Okay, let's go from this to phase. Surface plot, phase plot, great. But we can code the phase plots. So let's take a look. First, phase plot of sine of x plus iy. This is now the phase plot, the same function we just looked at of x plus iy, okay? And here we go. We're zooming in. That's all we're doing. The same function's being coded the whole time, and we're zooming in, zooming in, zooming in. And as we do, the phase expression bunches in different ways. I'm sure you're noticing sometimes they're aligned in colors, right? There's like a periodic coloring of the rainbow thing happening there, and then not rainbowish, and back to rainbowish. You can tell how we're zooming in here towards, maybe you're thinking of an x-axis or something, but ooh, something changed there, right? Something changed, and now it's just like these rainbows that we're zooming in on. There's no more of the phasing stuff that's happening. Interesting, there was a cutoff to the phasing. This is more like what we're used to seeing. I mean, you can probably relate this scale to the sine function you're used to, right? That graph there. So if I zoom back just a little bit. Let's go like right there, right? There's a sine graph we're used to. Okay, at least you can kind of connect to it. But look how different of information we're getting here. It's very unfamiliar kind of information, but very different, right? What?
Yeah. Well, it was interesting because there was a certain point where you went up so far, it just seemed to be doing the same thing, doing the same thing, and then at a very particular scale, it just stopped, and then we just zoomed in.
There's like a phase transition there. Yeah. Yeah. So let's look in another way. Remember, we can invert the argument. So now this will be the sine of 1 over x plus iy. All right, here we go. I think this is absolutely gorgeous.
Oh, it's a lot different at the start.
Isn't that beautiful? Look, we got this white line come from negative infinity down to this point. There's another white line. These are branch cuts here. And there's another one here, and another one here. And they seem to show up in circles, smaller and smaller, then smaller, then smaller, and smaller, but offset. Interesting. Between every branch cut, there's a roll from red to red. Right? On every branch cut. Every branch cut shows up in the middle of red. Interesting. On this scale, things are approaching chaos looking in the center. But do you really believe it's chaos now? Look at the structure built in. You can tell we're winding a lot of structure in this system. This is the sine graph. Now we're very close to 0. Okay? Beautiful. Let's do the hyperbolic sine of x plus iy. Ooh, this is kind of familiar now. The line's going the other way. Last time it was this way, in the middle. You okay?
Okay. You stuck on the couch?
But we're getting the same sort of pulsating between the rainbow arrangement and non-arrangement rainbows, right? There's a lot of, well, I don't know which words you're going to pick to describe this, but I'm seeing a lot of the strings lined up together next to each other, rolling around under phase.
Looks like it's almost forming forms there.
And it ends the same. Of course, at 90 degrees different, right? But just like the sine. The hyperbolic sine and the sine are just 90 degrees off of each other? Well, maybe. I mean, at least at the end it resolves that way. It was the structure before. At first approximation, at 90 degrees rotation via phase. That's a really cool thing to see, right? Let's flip it around. The hyperbolic sine of 1 over x plus iy. Yeah, now look at the branch cuts. They go off in like rabbit ears, rabbit ears, rabbit ears, rabbit ears. And they get smaller and smaller, but they change sides over and back and forth, back and forth. And again, between the branch cuts, you roll from red through the rainbow back to red, and in the middle of red is where all the branch cuts are. And as we zoom in, we go back to chaos. These things are very, very structured and ordered. Look! Extremely structured and ordered functions. This is the phase expression. So we're asking all the pixels, what phase are you at? Right? And you can think of phase like where you are in the rotation of the circle. Okay? Like, are you going up? Are you going down? Are you being pushed left, right? Which way are you going now? This is amazing. All right, so we've zoomed in close to 0, 0, and it looks like noise to us at this point. Okay, cool. We've gone halfway. Oh, a third of the way. Let's do the cosine. Absolutely beautiful and kind of familiar now. Huh. It's quite like the sine.
Whoa.
Mm-hmm.
Now is it going the other way? Oh, like, it's not very hard to tell. Which
It
way it's
seems
going.
sometimes be going this way and sometimes be going that way, right? There's interesting pulsations between the phases. And then we end up like this again. So something that's starting to get a little bit familiar. And the roll between red and red here seems to be so linear, right? Like there's a circle rolling along the plane, and it's got paint along the cylinder. And as it rolls, it always paints red ever so often, right? It's just rolled paint from here to here, and it just rolled around. It's a phase map of how some cycle has been expressed to fill out the plane. Let's look now at the cosine. Well, let's go to the hyperbolic cosine of z, because it's the most similar to what we just looked at. It's just rotated at 90 degrees again. Very interesting, right?
Yeah.
What's the overlapping happening here in the middle? You see this bar? It's different than the outside stuff, but it's like the same on the left and right. Huh. What does it mean?
Yeah, I can't imagine.
At this scale, you can imagine it though, right?
It looks like waves.
Yeah, at this scale, it looks like a simple wave. Here, well, there's a simple wave, let's see, but then there's a twist. It's like you have a Mobius strip and then you twisted it here. This is where the twist happens, right? Because yellow, yellow.
Yep. Mm-hmm.
So we got long strips, and they're rotated strip by strip by strip. Red touches red, touches red. You can cut everywhere along the white lines, the branch cuts, and try to glue things together. Okay, let's do, aren't they kind of pretty?
Yeah.
These will be a bit familiar now, so cosine, it's pretty fast. Cosine of 1 over x plus iy. I really love this figure 8 start. And it has a symmetric starting boundaries. These are the same size, and then the same size, right? The branch cuts in the middle of the red. This time, every time we zoom in, we hit the same size as we go. That was different than before.
Well, it's also very interesting. We talked about this a little bit the other day. It's like, why does it look like a figure 8 when we do that?
Mm-hmm.
It's interesting.
It has a figure 8 boundary in it. Or like the lemniscate of Booth, right? Which is related to the lemniscate of Bernoulli, but you inflate both of the bulbs until they're full circles instead of that lemniscate shape. All right. That was cosine, hyperbolic cosine. Also has figure 8, but this one has extending out of the figure 8, up and down, these branch cuts. And then just repeats, copies, copies, copies. But notice very specifically, this is quantized. This entire structure is quantized. You can see it radically right now. These are the quantum jumps from branch cut to branch cut, okay? This is really cool. This is in the hyperbolic functions already, right? Buried into their phase. You can think of it as being buried into numbers in a way, because this is buried into the structure of complex numbers. Right? Cosine and sine are part of the complex number construction. Very cool. All right, now we have the tangent. Let's do, something different. Interesting. We zoom in on the tangent. That looks more like what I thought the cosine or sine waves would have been. But of course, this is the phase plot. Phase plot. Sine over cosine, right? The tangent. This kind of looks like we got the sine in it. This is like a derivative related plot. That was a beautiful one. Let's do its hyperbolic version. Wow, that's different. First of all, 90 degrees different. And?
It's, it seems to be doing a lot of changing.
And it's very red on this side. Mostly red and sometimes all red. Not a lot of blue. Blue's all over there. Interesting. And it looks like it's just doing random kind of noise phase. Oh, that was really red there. Oh, look at that.
It's going through, and you can you can see texture on the right hand side. So it's a tangent thing. That does seem to be some actual.
Interesting. Now you're starting to see in the center the wave. We get down to scale of 1 here. Interesting. Okay. These graphs are far simpler to try to decode what's going on, right? I will, in a way, certainly at the point where we've zoomed in to the simplest part of what's going on. Let's look at the tangent of 1 over x plus iy. Another pretty display of color. And look at the inversions of phase that bubble down smaller and smaller and smaller as we go inside of the first inversion.
It's like we're driving down the road.
Yeah. There's a perspective effect, doesn't it? It's really cool. If you look, you can kind of see the ribs extending from these guys, barely faintly above and below, but it's mostly just solid color. The little bit of ribs extending.
Now it looks like Nebraska.
True. Okay, and then let's do the hyperbolic tangent of 1 over z. Yes, this is one of my favorites. It's gorgeous. Look at the pattern of the branch cuts. We go off to negative infinity off the left. We come zooming in and we run into this string of concentric half circles above and below. Right? Waving in. It's just these waves the whole time. But look how it's ordering the system as we weave in, weave in, weave in. More and more twists, more and more twists, more and more twists.
It looked like a circuit for as it was coming into play, and now it's just.
Yeah, there's a lot of grids, first of all. See all the grids going exactly like that everywhere? There's a lot of cells in that grid, and the cells are combining to make these interesting patterns. Like there's a lot going on in this construction as we zoom in. It's gorgeous. You have to watch it several times for your eye to really pick out many of the different details, because it depends on exactly where you're looking when. And by the way, if you're watching this online, go widescreen for these. It's really worth it. Go widescreen. They're high resolution. You need to look at these details. It's amazing the structure in these simple hyperbolic functions. The ones we're all familiar with, the ones that are already on your calculator. Okay, beautiful structure. If you haven't seen them this way before, I really recommend it. There's some beauty there that's worth enjoying artistically alone, just to enjoy the beautiful artistic structure of these functions as you zoom in on different scales. The colors are gorgeous, but this is even more beautiful in a richer and deeper way, because we're talking about the functions that connect numbers. We're talking about the functions, at least the simple parts of the connections, the pieces that we can pull it apart as, okay? the simplest representations of the connectivity in circles, hold circles together, and so on. These are the functions related to all of the structure in numbers, the simple ones, right? Getting to see them means we're seeing some structure. We're seeing at least a slice of some structure in the connectivity of the field of numbers, the field of physics. It's the same field, right? It's the division construction logic of reality. This structure, right, is something now we can see directly by looking into the phase. I think it's an absolutely gorgeous thing. By the way, I also recommend looking with Wolfram Alpha at the surface plots at all different scales of all of these basic functions also. Okay, and to advertise for what's going to be coming up, this is kind of preparedness. I think I'm going to, in a video coming up next, we'll review the concept of what we're trying to go after right now a little bit more richly, and maybe go over one column in the constants of nature pattern we got there, to derive a couple of them, but to discuss maybe the pattern that we see there. But also then we're going to talk about how that whole pattern, all of it, is based on 5 hyperbolic divisions, 5 hyperbolic structure limits that are defined by the Planck constants. In fact, I think I got them right here. So we have 5 equations using these hyperbolic functions only, okay, to connect or to define the boundaries of our hyperbolic division structure. We have 5 divisions, ways that we break things up hyperbolically, and we're balancing them all together, and we're assuming it's exactly these, because these are defined in our Planck constants. And those Planck constants, those 5 hyperbolic constructive balances, just like the 5 pieces in the Dirac equation being set under hyperbolic closed simple balance, those 5 limits give us all of the relationships in the constants of nature. All of the relationships in the rules in physics are directly coding built-in features of those limits. And this is really exciting, and what we're going to do next time is we're going to look at the phase plots of the 5 hyperbolic boundaries we call the Planck constants. So the phase plots of the Planck constants come up next time. We're also going to review more, probably in detail, at least one of the columns in the list of constants in nature. So that's what's coming up. We're still trying to learn everything we possibly can over here, and we're looking into all kinds of ways to interpret the structure here more richly, which mostly involves us learning more concepts. So we're spending most of our time upping our game with learning the features, following the clues of what we got out of the constants of nature, and taking those clues as seriously as we can by learning all the concepts that people have already uncovered related to those clues. Next time, look forward to phase plots. You saw how gorgeous they were this time. This time we're going to take the way that nature takes the hyperbolic functions and puts them together, right? It's not just going to be on a flat plane. We're going to not just use the sine by itself or the hyperbolic sine by itself. We're going to modify a little bit to fit things together, but we're going to have just 5 hyperbolic functions, all of them very short and simple, and we're going to see those in phase, and they're going to be mind-blowingly beautiful. Anyway, so that to look forward to next time, and yeah, I think that's now it for real.
Cool.